Hello, all. Can you hear me? We will start now. So I think this will be the last session. Um, right. So we will discuss today's problem session is on reinforcement learning and learning theory. Um, right. So what I'll do is I'll quickly go through some basics of what reinforcement learning does and what we do typically. We'll not go in detail. Regarding learning theory aspects, we will go through a little bit detail of pack learning and we show that we prove some uh, small thing theorem in a realizable case. So I'll tell what is realizable and all. Okay. So let me share my screen. You guys can see the screen, right? Okay, so let me quickly go over the RL. I will not spend much time on this. Okay, basically, this is different from your supervised or unsupervised setting, right? So, this happens in, you can imagine it happens in a real time, right? So, where you keep learning um depending upon your past, right? By penalizing on how you have performed based on your decisions. Okay, so the typical setup you see in RL is this thing. Okay, a very popular diagram. You might have seen this in the course as well. This is an agent. There will be an agent. Okay, that is supposed to take actions, and there is an environment. Agent interacts with the environment. Okay, and you take some action here, and by taking action, you move to say next state, and you get a reward. Okay, so here you may have uh, say at time t you have say state t and rt. This is the input to agent. Okay, so this is an RL setup, right? This is very different from your conventional learning, supervised, unsupervised, semi-supervised, or self-supervised, right? This is totally different. um right. Now what agent keeps interacting with environment based on what he receives an input. So these inputs are states, right? At what state that agent is in and what reward he got by taking a previous action, right? And depending upon that, agent takes actions, right? So that is nothing but policy. um, Policy is typically denoted by your pi, and this is an action given in state t and say Okay, so this can be probabilistic or deterministic. Okay, that means let's say you have actions a1, a2, a3, a4, and you have states s1, s2, s3, s4. So by probabilistic, what I mean is if you are in state s1, right? Let us say s1. So there is some probability that you will select action a1, and there is a probability that you select action a2, right? And this all sum to one, right? So that you should be aware. But deterministic, what I mean is if you are in state s1, right? The probability, let's say your policy is such that you always choose action 3. This is one, right? So that is deterministic, and this is um, so what is your end goal? End goal is you have to maximize your expected rewards. Let's say time t. I mean, if let's say assume you are doing this for a finite time, right? You have to maximize this thing, expected rewards, and typically you keep playing. Uh, there's no uh, hard and fast rule that you have to play for finite time steps. So suppose there is a game like chess or something, right? So it happens in finite time. If you win, you win, right? So and there will be another thing, right? Something a balancing of a say pole or something, right? Uh, right? You want to keep it balanced, right? So this will keep go on, right, till infinity. So yeah, this is what I would like to touch upon. Arun, I will not go into detail because the kind of questions you have it are very elementary, at least on the assignment side. Okay. Um, okay, so we will go into some more details on learning theory a bit. Then we will solve problems. I mean, you should find it trivial after whatever we have it, uh, whatever we discuss now. Right. So yeah, basically what happens is in learning, you typically data whatever you have this data, right? They draw from a distribution. You assume that your data is coming from distribution, and let's say some labeling function is there, some ground truth labeling function is there, right? And typically if you know the data distribution, right, so your base, you can use the base rule and find the best predictor. And but the problem comes is you don't know the underlying data distribution from which the samples are drawn, right? So learning theory deals with the guarantees that under certain assumptions of your hypothesis is a set of predictors, right, from which you have to choose to minimize your training error, right? So basically the goal of learning theory is you want to minimize this loss, right? Data is coming, right? You want to minimize this thing. So let me tell you what is this notation means. D is the data from which the distribution from which your samples are drawn, and F is the ground truth labeling function that you want to predict. You don't know. Basically, what you are given are Xi's and Y's. Xi samples, and Y is nothing but some labeling function which you don't know. So your goal is to find this F, right? Given some finite number of samples. These are finite. Okay, so you want to minimize this thing as low as possible, but since you don't have access to D, you only have access to a set, training set, typically denoted by SX. Okay, so you only have samples to this thing x1, x2, and so on xm. Right, these are drawn from uh, D. If there's a distribution, you keep sampling from the distribution, you get this finite samples, and there is underlying function f of f that labels this thing. Right, you don't know what is f and you don't know what is d. All you see is x1 to xm, and you want to predict f. You can't predict d. Okay, that's even more tougher problem. So you only want to predict f. So for this, what you assume is, you assume some function class h. Right, there's a bunch of functions, say that can be a set of neural networks, right, and say it can be a linear regression kind of a thing, right. Your h is nothing but set of, if it is a linear regression, right, your h is nothing but all the possible sets of w's and b's, right. From this h, so basically for a tip, we are only dealing with the pack setting that is nothing but probably approximately correct. Pack setting, so that means, uh, what there is an assumption that there exists uh, there exists a h belongs to h for which ld comma f, the error which you want to minimize is 0, right. That means let's say these are positive examples, and here you are negative example. That means there exists a separator, right, that can successfully label the positives and negatives. Right? That's an assumption you're doing. Otherwise, you cannot solve this problem. You need to have it some assumptions, underlying assumptions, right, on the function class h. Um, all right. So what we are given is this s, and what we want to minimize is the training error, right. So we want to minimize how you have predicted on a particular example, let's say xi. This is not equal to f of xi, right. If it is not, this will become 1. I is nothing but an indicator. You have m training examples you saw, and this is sigma I is equal to 1 to n. Okay, this is denoted by ls of h, right. Now s denotes your training set s, as I defined here. H denotes a function class that is picked up from this h, and this is nothing but your training error. Okay, so if you minimize this thing, ls of h over h, right, let's say you got this as hs, right. What we want to know is, by minimizing this training error, on by minimizing this training error, what you want, that is the output of this minimization is hs. S denotes, you minimized it on the training set s, right. So what are we interested in, how this thing generalizes to unseen examples. Okay, so this is the main problem you want, right. So you want to evaluate what is the probability that this thing can be more than epsilon. right? This is your error probability. So here, right, so typically you evaluate your probabilities on random variables, right? So what is random here, right? What is random is your HS is random, right? Because your training set is random. You just sample it from your distributions, right? um right, so yeah, any questions? I know I'm moving fast, but yeah, uh, any questions that I can answer at this point? No questions? Yes, this is focused on assignment, not assignment 12. I think basically we have got a set of problem sets uh, that we are supposed to explain in these sessions, right? So the problem set is on this learning theory and reinforcement learning. So that's why I'm just going through the some basic stuff before going to the problems. Okay. So yeah, so let's make it. Let's go in detail. Right. Let me add the. Right. So we want to compute this quantity, right? LD of H S greater than epsilon, right? So yeah. So what pack learning guarantees is, now there exists a numbers epsilon and delta, right? This is function from, let's say, uh, R2. Epsilon is a real number, delta is a real number to a natural number, right? When your m is greater than this m epsilon comma delta, okay, so with probability of um, over this probability is over sm, right? At least 1 minus delta, we you can guarantee that this thing will happen. LD comma f of hs is greater than epsilon, sorry, less than epsilon. If it is greater than, if your m is greater than this, you can guarantee that this quantity is less than epsilon. So basically all, I mean, I was planning to go to prove this, but at least in the pack setting, but let me give more intuition than going to the proof. What we are trying to do is, so what, we have a training set S that is drawn from a distribution D, right? And you have a test set that is also drawn from your distribution D, right? So training set is nothing but a finite number of samples, x1 to xn, and you can draw any infinite number of samples. So what we are doing is, from this training set, right? If we do, if we learn using an ERM is nothing but your empirical risk minimization. That is as good. That is nothing but you compute error on each sample and then average, right? And when you do that, you get some learning function H. For example, linear regression, you assume W transpose X plus B, right? W transpose X plus B, right? You minimize mean square error and you get some W, right? That I'm calling as HS here, because that is obtained by minimizing your training samples, error on the training samples, right? The question we are trying to ask here is, if I learn this thing, would it be suffice to guarantee that it also will this also generalize to unseen samples drawn from the same distribution, right? Not just this x1 to xn. Right? If I again draw, right, we'll be able to generalize. So what we are guaranteeing here is, if we want this thing, right, probability of this thing to be less than epsilon, right, this error, the test error, on any randomly drawn this thing, right, test samples. So what we are saying is, if we have a minimum number of, there is a number, if my training sample is more than that, I can guarantee that my error, test error, will be less than epsilon with probability 1 minus delta. This delta is over the choice of this training set. Okay. Okay, so this is nothing but your pack learning, and this should work for any distribution, not just Gaussian or something distribution over the data. Okay, any distribution. If you can find any distribution for which this doesn't hold, then it is not pack learning. Okay. Okay, so let's not go to the proof. We will go to, I think this background should be good enough to solve this assignment. Okay, so let's go to the problem set quickly and solve. uh, where are we? Yeah, here here we are. Yeah, so this is what, as I would just described, right? Generalization error. When you draw samples x y from a distribution D, there I drawn only x, and I assume there is a deterministic labeling function f that can predict your label. But this is agnostic setting, where you draw both the data and labels from underlying distribution which you don't know, right? So what is D? Right, D is the distribution, right? Typically we don't estimate distribution, but yeah, this is the most relevant answer here. Okay, so answers can see a sample of the underlying distribution. That is wrong. What is a sample? Sample is this thing x and y. This is one sample. A different distribution that that we are using to estimate the true underlying distribution. No, this is also a wrong answer, and this is too far. All right, and yeah, as I have explained through a through a and through an example of linear regression, that W transpose X, right? Now, what they are saying is hypothesis functions obtained by ERM, that's which I described, E of H. There I describe as LS of H, right? And you minimize this error by choosing your H from your set of hypothesis classes. That H can be linear regression, neural networks, or whatever. If H is a class of neural networks, what is this set H consist of? Different layers, different neurons, different values of weights, or different inputs. You guys can type in these questions, because I explained this using a set of using the linear regression example. It's the same answer. You guys can try typing this. Yeah, C is the correct answer, because your hypothesis is determined by the weights of your neural network, or any regressions, or anything. Okay, so yeah, next question. Yes, so of opening bound for a classifier H indicates how close, right? So E of H here is your the true error, true error in the underlying distribution error, and epsilon h is your training error or the population error, or sample, let's say training error. Right? What is this showing is how far you can be from your true error, right? If you are more than say gamma, that is upper bounded by this the right side inequality. Right now, if you find, the question is, even if you increase the number of samples, doesn't give your estimate, it doesn't improve your hypothesis. What is the problem? Okay. Any answers? D is one of the answer, and C is also an answer, because um, what I have just explained is, um, if if the hypothesis class is learnable, right? Um, then if you sample, train, and test from the same distribution, uh, right? Then uh, increasing the value of m can drive your error as close as possible, right? As low as possible. But if that doesn't happen, that means, what is happening is your choice of hypothesis itself is incorrect, right? So this is what is an underfitting problem, right? If your model, let's say if you are needed a neural network and you used linear regression, no matter how many data samples to give to that linear model, it will not learn, right? So because your class is not powerful enough to learn the data, right? So that's one of the answer, that there is C, and that's why it is C. And the samples are not IID. We always assume this samples to be IID, and we minimize accordingly. We are moving to, yeah, we are done with learning theory. So any more questions now? From now, next 5 questions are from RL. Any more questions regarding this thing? Any more questions, guys? You can type in. I'll try to answer. Okay, so then we will go ahead with the RL part. Okay, so right, so there are two statements. One is RL and unsupervised learning, and RL learning doesn't have any labels. Which one is true? Just take a minute and just type in your responses. Okay. Hmm. Okay. So basically, see, as I explained, right, RL is now. Let me show that slide and talk. Right, RL is not an unsupervised learning. It is different from that. Unsupervised learning, you have data and you don't have supervision of that data, and you keep trying to discover some structure from the data. Right? That is unsupervised, right? And RL doesn't have any labels. Basically, you perform some actions. That action interacts with environment. Based on that action, environment throws you in some state, a next state, and it gives you some reward. Basically, you keep improving your actions so that you maximize your rewards. Right? So there are no labels, and it is unsupervised learning. Right? So that is D. And yeah, so there's another question. So it seems like aliens challenge you to a complex game that no human has seen before, and they give you time to learn the game and develop strategies before the final showdown. Okay, you choose to use machine learning because an intelligent machine is your only hope. Which machine learning paradigm is best fitted? Right. So what is this? Please go back to previous question and explain once again. Okay. So yeah, C is the right answer. That is RL. Yeah. So this question is like they're asking, is RL an unsupervised learning? Right, and statement B says RL doesn't have labels. Right, so the first answer is wrong because it's not an unsupervised learning, it's a different learning paradigm. B, you don't have labels in RL, you interact with environment, and environment gives you a reward. Right, reward is you quantify your satisfaction by say some number. Right, and because nature doesn't throw you reward, right, it gives you something that is reasonable to you. If it is not reasonable, you can give negative rewards. If it is reasonable, you can give you positive rewards, right? Right, so that's how you learn, not through the explicit labels like supervised learning. I hope that that answers. Did that answer? Okay. And yeah, this is a simple question. And yeah, this is an explanation for that. So when there is no expert rule for you, right? As if there is expert, you can take supervision. If there is no expert and you are supposed to learn by interacting with environments, then RL is the optimum, the best learning strategy. Okay, so in this famous dog experiment, right? Um, what is the input signal to dog and what is reward? Mm, signal and reward. Right, that's bell and food. Yeah, that's right. Mm, what is a policy in reinforcement learning? I explained this thing. Uh, you can tell me what is mapping, what is the policy, how it is defined. The mapping from states to rewards, or state to actions, or action to next state, or what? C. C. No, no, that's not right. Right. I just explained that in RL, your policy is the mapping from states to actions. I also explained it can be probabilistic or it can be deterministic as well, right? And that action interacts with the environment, then environment moves you to a next state and it gives you a reward. With that reward and next state, you again take an action. Your ultimate goal is to take such an actions where reward is maximized. Okay. Okay, so but why not B? What is B? No, it's not right. It is not mapping from state to reward. In a state, given a current state and reward that you have obtained by taking previous action, right? Your policy must be to what should I say? In this state, what action I should take? That's it. That's how it is defined. Mm, okay, so yeah, final question. You want to make an RL agent for a game where two players compete, right? Which among the given would be best approach for this? So you can see right, option A, play against best human players. If you choose that option, your model can get as best as the human players, probably the best human player, right? It can learn to mimic the best human player, right? And let's say your option D, watch thousands of games being played and learn patterns in an unsupervised manner, right? This is also an unfeasible option because I mean there can be so many possibilities, right? That um, I mean you can only capture a finite number of possibilities in this fashion, right? So 1,000 game possibilities. Right now, play against a supervised agent trained on demonstrations of best human player. This will also limits your capability to the best player, right? Right. So option B is reasonable because let's say you performed uh, with capability C, right? Now you try to beat that, right? So now you have improved your version, right? Now try to beat that, right? So that's a reasonable approach. Okay, so yeah, this concludes your problem solving session on RL and learning theory. um, yeah, so I think that's all I have for today. So you guys let me know if you have any questions. We can stay or we are done. So I think this is the last session for this course. It is from my
Yes,
side.
sir.
Probably a couple of more will follow.
Yeah, sir. I have one question actually in week 12 assignment.
Yeah, yeah.
So we have got the solutions as well. Can you
Okay.
explain actually how is this margin is calculated as 0.05? I just ping the complete question and the solution as well.
Yeah, I'll try to answer because I haven't seen that assignment. Yeah,
Yeah, yeah.
please.
I pasted the answer as well actually. If you let me know if you're not able to see, I can ping the answer again.
Yeah, so you want to toss a fair coin a number of times and obtain probability of getting hits by simply taking average. What is the estimated number of coin toss? What is the estimated number of times you will have to toss the coin to make sure the estimated probability is within the 10% of the actual probability at least 90% of the time? Okay, so
It's basically the Chernoff inequality is what being used, but only thing is how are we calculating the margin is what actually I could not get it.
where is the margin here?
See that 0.05 is the margin is what uh,
So
is
that
given.
is what they have given as a solution, is it?
Yeah, yeah. In the solution they've given that.
So okay, let me try to. So basically, you are they have given. Okay, where is that? Yeah, you're tossing a fair coin. That's why your P is 0.5, right? That is, I think you are clear about that. And your X is nothing but the average number of, say, if you're estimating heads, right? Number of heads by total number of thing. That is your X. And what you wanted is this thing, right? Greater than 0.05. This is what you wanted.
Yeah. Yes.
Mm, is within the 10% of actual probability. Yeah, basically, what is actual probability here? Actual probability is 1 by 2, right?
Yeah, that's 0.5. Yes, for
Right.
a head.
And
Hmm.
what is 10% of that?
Okay.
Right. So that is
Okay.
0.05. That's how you got that number. And you
Oh, oh.
want it, and you wanted it within that, right? So
Hmm.
probably somewhere you would have taken 1 minus of this,
Hmm.
right?
Yeah.
So yeah, think that's what it is. And why it is point 0.1? Because you wanted this probability to be within 10% of actual, sorry, at least 90% of the time you want to be within that. That means
Hmm.
10% of the time you are more than that, so that's why they have calculated that, right?
Yeah.
10% you are more than this difference. I hope it answers the question.
Yes, yes. It's on. Thanks, sir.
Any more questions I can try to answer?
Can I ask a question from previous week, sir?
Yeah, I'll try to answer. Yeah, if I can.
Yeah, basically it's something related to factors in a Markov network, actually. So they've given, yeah, maybe, okay. So this is what actually they've given. They've given four random variables and a set of factors, and they
Ah,
want us to draw the Markov network for that.
right.
So normally, how do we approach this? If you can give some hint or something. I mean, we have the solution as well, but just
Basically, you
because
see, it
that's
is
an image, right?
Markov network is nothing but your undirected graphical model,
Right.
right?
Hmm.
So, how should I put it? And your factors are typically the maximum. They are nothing but cliques,
Yeah, maximum clicks.
right? The
Hmm.
clique is nothing but the minimum, not minimum, the maximum. nodes that are connected completely, right? That
Hmm.
you should keep in mind. When you put A1 A2, it's a click,
Hmm.
right? So you can't put A1 A2 A4 in one go. I mean, they cannot be connected, right?
Yeah,
So
but actually in the solution, it is completely connected. So the solution says that so A1, A2, A4 are the three interconnected with each other, basically forming a uh, three click. And similarly, A1, A3, and A4. So basically, only there is no edge between A2 and A3. So that is the solution what is given here. Actually, there is no explanation as such.
even I'm not sure why is that. You are saying A4 and A1 is also A4 and A2 is also connected.
Yeah, yeah.
But
Basically, maybe if you can put A1, A2, A3, A4, I can tell you what are the edges there in the solution. So maybe that can give you little more
yeah,
clue.
let's try this. A1, A2, and
Two,
A4, right?
A3 and A4. Yeah, A1, A2, A3, A4.
A3, A4, right?
Yeah, you can
So
make a click with A1, A2, A4 with three
A1,
edges.
A2, A4. Okay, but I
And
don't see A2, A4 there,
yeah, but yeah, that's
right?
what.
So this
And there is
so this should correspond to this guy, some function of A1, A2, A4. But yeah,
maybe
I
is
mean,
it
if they are
like
not giving that, so you can have to assume that, right? Psi of this A1, A2, and
A2,
psi
A4?
of A2, A4. Yeah, this can be product. You can do this kind of thing,
Hmm.
right? So yeah, so that
And the
means
other
given
click
A2,
actually,
that means
yeah.
given A2, A1, and A4 are independent, right? This is by making it this way,
Hmm.
you are um, what should I say? You are assuming some more structure into that, right? So
Hmm.
yeah,
Similarly, there is a click A1, A3, A4. So that is also there in the solution.
A1,
A3 and
A3,
A4.
and A4.
Yeah,
Okay.
and there is no edge between A2 and A3. So this is a solution what's given actually.
Hmm. So there is A2, A3 there in your option.
In the question, sir,
A2 and A3. There is no edge in A2 and
there
A3.
is no. There is no factor A2 and A3. We have A2 and A4 and A3 and A4, but not A2 and A3.
Is there, A1, A4 is there, A3 is there, A2, A4, A3, A4. Yeah, yeah. What I did not get. What is the question then? This satisfies that potential equation, right?
Yeah,
This
no,
graph.
this is a solution. The
Yeah.
question is actually what is the Markov network? So I was asking how can we draw that actually?
Basically, you try to put all edges that are given in potential functions. That's the least you can do.
Okay,
Just put an edge. That's it. Undirected edge.
okay. A1,
That's all.
A2, A1, A4. Okay, okay. Yeah, thanks.
Okay.
I don't have any more questions.
Okay, guys. Then, yeah, maybe we can sign off if you don't have any questions. And all the best for your exam. Um,
Thank you.
okay. Bye, guys.